solve for C for you. The next exponents, that's in half years. I further know that that's our initial condition. Population at time 0. The population at time 0 is going to be exactly equal to C. That's where that comes from. So we know that we found that we found C is 1,000. Notice how that works from what I just talked about. That's the initial population of 1,000 bunnies. How do we know that? Well, that's what we started with. And we plug in time equals 0. That's we start with 1,000 bunnies, and that's useful. So we still here. Does it make sense to you that the first step we should do is divide, and we'll get 3? It's triple. It's the days, the K we're looking for. T is 1 because that's after 1 year. Does it make sense to you that the first step we should do is divide, and we'll get 3? It's triple. It should be 300% increase. It's triple. E to the K. So now we're going to have to solve for K. Remember your logarithms. Remember your natural log. Let's just do a natural log on both sides. So K equals ln 3. And if we plug that back in, to what we already had, 1,000 e to the kt becomes 1,000 e to the ln 3 times t, because our k was natural log of 3. So let's go ahead and let's find let's use this to find the population in a little while's time. So if you want a little recap, we start with the differential equation, we solve it somehow, or it's given to us, we verify, immediately verify. After that, we know we have a general solution. It's going to take 2 pieces of information. One is going to be, well, an initial population. So at time 0, how much did you start with? That's going to solve for C for you. Next, we'll need what happens in a little while's time. So some definable amount of time, like 1 year, 2 years, 1 month, 1 minute, whatever it is. Plug that in, and it's going to let you find your K. Now we can use this for practically anything. How many bunnies are going to be around in 3.5 years? Probably a lot. So let's find P of 3.5. One more thing you might want to do, just to make this not as obnoxious here, you can do some mathematical razzle-dazzle with that. If you have ln of 3t and an exponent, remember, I'm going to do a little sub-note here. Remember that x to the m times n is x to the m to the n. You go, well, what's that do with anything? E to the ln 3 times t is e to the ln 3 to the t power. But because you have e and ln composed on one another, is e to the ln 3 to the t power. But because you have E and ln composed on one another, you have inverses in the composition. These are gone. You're going to get 3. So you can rewrite a lot of these by just doing, well, this is going to be that's a crappy t. 1,000 times 3 to the t. That makes things a lot more concise. So where'd that come from? Well, you have a multiplication of exponents. That's an exponent raised to an exponent. E to the ln 3 is just 3. So you have 3 to the t. Try it both ways if you'd like. See if it actually works.
Keegan really enjoys telling people that she was a St. Jude patient. She really, really enjoys telling people about her being on St. Jude's TikTok page. Keegan,
I'm begging you right now, just please don't multiply those and get 3,000. Bacon, okay, just bacon. That breaks order operations, exponents before multiplication. You'll notice I have 3.5 is still the t because I want to see where it comes from. Now if I want to find out how many bunnies we got in 3.5 years, just plug in 3.5 for that t. Oh my gosh, if you did that yourself, 3 to the 3.5, I hope I did my math right. 3 to the 3.5 is big times 1,000. I have 46,766 rabbits. Or thereabouts, if my math was right, I did it quick. But that's a lot of bunnies in 3 years. They're bunnies. I guess they do stuff. Anyway, so rates of change, that's what differential equations are in the first place. So these are just with respect to time. Populations, things that grow over time. That's what a time rate of change is. It's a differential equation that's specifically geared towards time as the independent variable. Done exactly the same way as far as verifying, done exactly the same way as far as you need an initial condition to find a particular solution, in this case to eliminate your arbitrary constant. That's exactly what we were doing last video. The k part of it, you need something else for that. So you need where are you in a finite amount of time. That will let you solve for k after you have used your initial condition. Use that first. Then once you've found the constant, the arbitrary constant, and the constant of variation, your k, you can use it for lots of things. How many bunnies are you going to have in 3.5 years? Lots of bunnies. Or they're all cute. Or whatever else you have. How much are you going to have in 20 years if this holds up? Now, later on, we're going to talk about stuff like a limiting factor on population. There's a carrying capacity. We don't just get to multiply forever and expect that the same area is going to sustain this population of bunnies. So there's going to be birth rates and death rates. This would be the case if none of the bunnies died. Well, we know that bunnies do die. And more bunnies are born and things like that. So we're going to have some more robust examples later on. This is just to get your feet wet to understand differential equations as they relate to time. I hope that made sense. I hope that you guys stick around for the next ones. We're going to start learning how to actually solve some differential equations from scratch without being given the solution next time.
Want to ace AP and still have time for you? UWorld's AP courses turbocharge your study time, giving you more time for friends and fun. Our study guides simplify.
Welcome to another video. This one's kind of exciting because now we finally get to start solving differential equations on our own. The past few videos, all we've really done is kind of identify what they are, how they kind of relate real life things, and then how to check whether an equation is a solution. But I never told you where the solutions came from. We're going to start right now. And we're going to start with the most basic of differential equations. If you remember, a differential equation is just an equation that has a derivative of some function in the equation and some other junk. Sometimes the function itself, sometimes second derivatives, all sorts of things floating together. Our idea is to solve by finding the equation that satisfies the differential equation. And that's generally a family of curves. We're going to talk about that right now. So the most basic case that we can have in differential equations is when we have a differential equation with a derivative and just a function of x. So this is a differential equation. That's your derivative. A derivative of y with respect to x, or independent variable, equals some function of x. And here's the key, with no y's. So no y itself, no function of y, no first derivative, no second derivative, just the derivative isolated on one side and a function of x on the other side. If you have this situation, or if you can make this situation, you manipulate your problem a little bit, these are the most basic types of differential equations. In fact, pretty much all of Calculus 2 is based on this idea. So every time you did an integral in Calculus 2, you were kind of treating it like a differential equation in a sense, because that's exactly how we'd solve it. If you just have a derivative of the function you're trying to find, and it's equal to some function of x, no other y's in there, well, then we know a little something about derivatives. We know that if we do an integral will undo a derivative. And that's how these most basic differential equations are solved. Let me show you a little bit of math behind it, and then I'm going to show you that these can be done that way. So we have a derivative equals function of x with no y's, derivative function of x, no y's, derivative function of x, no y's, derivative function of x, no y's. Same thing for the last two. Derivative on one side, function of x on the other side with no y's, no y primes, no double second derivatives, just an isolated derivative and a function of x. So what I mean by why integrals work so well for this, we're going to see some funny math. If you remember where a derivative comes from, it's this idea that y is changing as x is changing, and this distance that you're changing is really, really little. Calculus 1 teaches us that limit of get really, 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 really close to something else is this idea of a limit. Well, these come from a delta y and a delta x, and the way that you start with your derivatives is that delta x is actually on the other side from a delta y. Because of that idea, we can move this around. It looks really weird, but we can actually write this worst dy ever. We could write that as dy equals f of x dx. We can treat them like they're separable, like that dy and that dx are just pieces that we move around. They come from the fact that we have the delta x, delta y in a limit, and we take the limit as well, you know what we take. As we take that limit and the delta x's get really, 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 really little, we call that the differential. So we're going to talk about differential forms of differential equations much later, but we need to know that we can move around dy and dx's. We can separate those things. Now, because we have this idea of an equation, you can do whatever you want to an equation as long as you do to both sides. We can actually take an integral of both sides. So if you take an integral of dy, well, think of that as 1 dy. Take an integral of 1 dy. Let's see, dy with respect to y. You're going to get a y. Take an integral of f of x. Remember, this has no y, so this is solely based on x, which is why this works. Why it's so simple, why integrals work, is because you're able to separate the dy and the dx. On the left-hand side, integral of dy gives you y. On the right-hand side, integral of f of x, because that has no y's in it, because it has no second derivatives, first derivatives, nothing like that. This is typically, if it's possible, it's a basic integral of f of x. So straight out of Calc 2. And I've chosen some problems up here that's going to help you remember some of the techniques about Calculus 2. So we're going to have some integration by parts, substitution, some trig sub, stuff like that, just to get our brains wrapped around it. This is more practice than anything, because the idea is very basic. The idea is, if you have a derivative and a function of x with no y's, separate the dx and do an integral. That's practically it. And if you get that, you're going to be fine. So let's do it. The integral of f of x, well, you'd get some antiderivative there. But what you're also going to get, and you remember this because your teacher yelled at you every time you didn't do it, you get a plus c. And we spent a lot of time talking about that plus c. We talked about how that plus c creates this general solution. It's an arbitrary constant, and it creates a family of curves. each of which is going to satisfy this. If you take a derivative of this right here, you're going to get the derivative of y with respect to x is equal to, well, the derivative of the antiderivative, obviously, but then the constant, that's a constant, it's going to go to 0. It's going to give you back that for any choice of c that we have that's a constant. That's the arbitrary constant idea. This is a family of curves. And what's interesting about this is that what these create are this family of curves that are, in a sense, parallel in that they don't intersect. Think about this for a minute. Plus c, if you add that on to the end of a function, all it creates is this vertical shift, up or down on the y-axis. It's not moving it left, it's not moving it right. It's just shifting it around. Same exact curve. It's just one right, think of a parabola, one right on top of another, right on top of another, right on top of another. They're never going to intersect. So we're going to talk a little bit about this after we do these problems, just to get practice, about the difference between a general solution, this, and the difference if you have one initial value. Because what's going to happen, I'll preview, I don't like suspense in math, you need to know what's going to happen. If you have derivative, function of x with no y's, take an integral.
The same prompt, two vastly different results.
Both sides, you're going to get a y, and you're going to get an antiderivative of the right-hand side. Use whatever technique you can from Calc 1 or Calc 2. What you end up getting is a family of curves. We call that family of curves the general solution. It's got an arbitrary constant. It could be any number, whatever, but it is a constant. If we want to narrow it down, here's the key for a particular solution. If we want to narrow it down, we need just 1 point. Why do we need just 1 point? Well, think about this. If these are all parallel curves in a sense that they don't intersect, then only one of them is going to go through any one distinct point. Because if they don't intersect, they never share any common points. Think about that. So if I give you a point and say, hey, I want the one that goes to this, there's only going to be one curve that satisfies that in this type of a differential equation, this type of a solution. That's what narrows down our family of curves into a particular. As you say, here's all of our parallel curves. I want the one that goes through that point. You go, oh, okay. That's going to create one particular solution. So we're going to do that in just a little bit. So let's start with doing some examples. I'm going to erase the board. We should have this idea down. The idea is if you have a derivative equal to a function of x with no y's in it, we're just going to move our dx and do an integral. That's it. Make sure you get a plus c. That's your general solution. So we're going to do these 5 examples on the board. Again, there's some different techniques. And then, so we can practice. And then I'm going to start putting up those initial conditions. All right, so here we go. So I've rewritten the problems, the same ones we had on the board just a minute ago. Let's go ahead and go through all the ideas of, we can still take integrals. There's some techniques. I've put 5 different techniques up here for you so that we're just kind of getting our brains wrapped around it. And then we'll talk about the initial conditions. So let's make sure that they fit before we do every one of them. In every case, we have a derivative of y with respect to x equal to a function of what we're taking the derivative of y with respect to. So here's the derivative of y, here's the independent variable, and this is a function in just the independent variable that is necessary for this technique to work. If you have any y's floating around over here, if you have any second derivatives or other derivatives in there, this is not the right technique to use. We're going to deal with a lot of different techniques, but this is a very, very basic one. You got a derivative on one side, function of x, or the function of independent variable on the other side. That's it. So what we're going to do in every case is we're going to move that dx. You don't really have to. There is a way to think about it. If you wanted to right now, take an integral with a dx on both sides, but then understand that because that comes from that delta x idea, it's getting closer to that delta x, change of x is getting closer to 0, but never becomes 0. It's okay to cancel that out. So you can actually do that. Most people do not do that. So most people think about this as, well, that's a little bit weird to think of. The math is kind of funny on that. But if we do just move the dx, which is possible, then we can take the idea of an integral on both sides. So this idea that, hey, just take an integral on both sides. Okay. And if we do that, on the left-hand side, it's really nice because you just have the integral of dy, or the integral of 1 dy. The integral of dy is going to give you back that y function that you're looking for in a differential equation. On the right-hand side, this is where all of your work is going to come in with this technique. You still need to know how to do integrals. You still need to know some basic substitution techniques, or your table of integrals is really helpful here. At this point in your math careers, I don't know who your teacher is, or if you even have a teacher. If you're just learning this for fun or whatever, maybe part of your job, or relearning it because you've been out of school for a while, that's fine. But most instructors, most professors really don't care super much about seeing the hardcore work on your techniques of integration. They care that you understand the idea. So whether you're finding the answer from a table of integration or you're crunching it all out, it doesn't matter. It really, for most of us, it really doesn't matter. The idea behind it's more important. So on some of these, you go, man, that's a substitution. Yeah, you're right. That looks
You're applying
looks like tan inverse because table of integration. Sure, that looks like, well, whatever that's going to be because of table of integration, or trig sub. It doesn't really matter anymore. So use what's easiest to you to get the job done for integrals. This one, you could use a u substitution and do u equals x minus 2, but because the derivative of that x minus 2 is just 1, man, we can just treat this like it's one variable and just do the integral like we normally would. So imagine this is just u. We would add 1 to the exponent, that's 3, divide by the new exponent. So 1/3 bunch of crap in here squared. The derivative of this is 1, which is why it works. Otherwise, we would start dividing by the derivative there. And the biggest part about it, what we're just talking about, is this is going to create a family of curves by that plus c. These are all parallel. None of them intersect. If you start adding different values of c, they're all stacked right on top of one another. And it's a family of curves, each of which satisfies our original differential equation, which I kind of messed up there. I want to write that back so you see what we started with. Because it says this. Here's a function that if you take a derivative of it, the derivative of this function is going to be that. And that's true. That's the solution to a differential equation. Let's do the next one. So in the next one, we still have a derivative equals a function of x, no y's, no nothing, pretty basic. So we're going to do two things. We're going to move the dx over, we're going to take an integral. I like to show this in 2 steps most of the time. You really don't have to. So if you move this over, you go, okay, that's dy equals x squared root of x plus 9 dx. And you go, let's do an integral of both sides. We could just put that right out front. That's fine to do that. Now, on the left-hand side, this is great. This is just going to be y. On the right-hand side, we'll have to have something else. This looks like a u sub to me. So if I take this as my u, then du equals 2x dx. I've shown several techniques throughout the, 14 years I've been teaching this stuff about how to do this with basic calculus. So whether you're of my school where you like to solve for dx and then substitute and cancel the x's, or whether what most people do is they will just solve for the pieces that show up here. So the 2's not in those pieces, move the 2. Then we replace the x and the dx with just that little piece. So here's our square root of u. We'll call that u to the 1/2. We know that x dx is du over 2. So when we do our integral, we've got this, hey, let's add 1 to the exponent. That's going to give us 3/2 over 3/2. But we had this 1/2 from right here. Well, that's going to be, well, these 2's are gone. We have y equals 1/3. Let's put our u back in there. X squared plus 9, but now this is to the 3/2 power. And then plus c is ultimately extremely important for us. Without that plus c, an initial value can't be used because there's nothing to plug in to test to find out what that value of c would be. So if you don't have plus c, how are you going to find that? It doesn't make sense. So you have to have that plus c. Also, can you check your work? Obviously, we should be able to check our work here. If you take a derivative, well, 3/2 times 1/3, that's going to be that 1/2. You go, well, how's the 1/2 going to disappear? 3/2 times 1/3 gives you 1/2. X squared plus 9 is going to stay to the 1/2 power, but then the derivative of the inside is 2x. The 1/2 and that 2 are gone. You're left with an x square root or 1/2 power. X squared plus 9 and the plus c would disappear also. So that does work. That's a general solution. You can check it with the derivative. Okay, next one. This one looks a little bit hard. At first, wow, I don't see a use of. You're right, you don't. But don't forget that there's a lot of techniques in calculus too. If we just isolate that dy, and we take our integral after that. We had a derivative of y equal a function of x. We do our integral. On the left-hand side, the integral of dy is just y. On the right-hand side, 10. 10's a constant. It has no bearing on the integration. Just pull it out, or leave it on numerator if you want to, or leave it on the outside. It doesn't matter. It's a constant. We're going to get 10. But right now with that x squared plus 1, yeah, you could use a trig sub, but if it's one of those basic things that's kind of been drilled in your head, like, oh man, something over x squared plus 1, that's in a table here, what would I do? Well, it's tan inverse. So if you have the table of integration, or you've memorized some of this stuff, don't be afraid to use that. We do need a plus c after the fact, though. And if we take a derivative of that, we do know that the derivative of this is that thing. So we're good to go. Next one, well, this is a little bit trickier. You could use a table of integration for this. We notice that it's a derivative. It's equal to a function of x without y's in there. That's great. If we separate out that dx, we notice that we can take an integral really nicely. The integral of dy again is y. On the right-hand side, well, that is in a table of integration, so if you want to look that up, that's fine. But if you don't remember it, or if you just want to practice like I do right now, you could do a trig sub. So we look at this and go, that looks like a triangle. It's not like a triangle, it's a square root. The math inside looks like a relationship between the sides of a right triangle. I always set up my triangles exactly the same orientation every single time. Now, many of you, if you didn't take me or you didn't watch my videos, you can watch them right now. It's in Calculus 2, it's trig sub, I want to say it's in chapter 7, but I can't remember right now. I don't memorize this stuff. What I do, I've never memorized it. What I do is I think through what would these sides have to be on a right triangle. If you're subtracting, then you're subtracting a smaller side from a bigger one, and that's got to be the hypotenuse. So 1 must be the hypotenuse. X has to be another leg then. So if you're doing Pythagorean theorem, you'd have the square root of 1 squared minus x squared is going to give you this side. So this whole piece is going to be the side of this right triangle. Then the square root of this is a side, and the square root of this is a side. What we want to do is find the hypotenuse first. Because you're subtracting, that's got to be bigger than that. Otherwise, you would have a negative inside of a square root. It wouldn't represent a right triangle. So that has to be the hypotenuse. This is going to be a leg somewhere, because the way the math looks is you've taken the hypotenuse minus another side. It's going to be one of these legs. So what we want to do is create a relationship where we have the hypotenuse correct, but then we also have this idea where we don't want a square root inside of one of these 3 trig functions: sine, tangent, or secant. So right now I know that sine looks pretty good if I put an x right there. If I put an x there, sine is x over 1. That's pretty nice. This last side.
Hello.
Do you want to play with me?
Sure. You want me to help you with your groceries?
Yeah.
This journey with childhood cancer comes at you in waves. Every day we wake up.
Isn't used in any of the trig stuff. It's used to get back your x's at the very end. So now we go, okay, hey, you know what? In this relationship, sine of theta equals x over 1. Now, if we're going to do a substitution like that, we need to know that because x's are independent variable, we're dealing with a dx, you need a dx substitution also. That comes from a derivative here. So if sine theta equals x, then take a derivative of both sides. Cosine theta equals dx. That lets us substitute. So we've already done the integral of dy, it's y. On the right-hand side, we still have an integral, we still have a 1, we still have a square root, we still have a 1 over that square root. We have 1 minus x is sine. So we have this sine squared theta inside, but dx, I kind of forgot something here, I need to make mention of this. When you do a derivative of sine theta equals x, you're going to get cosine theta, but I forgot my d theta. Now, if that makes sense to you, I'm going to show you something here. If that makes sense to you, like, oh yeah, it makes sense that d theta and dx are on opposite sides, then what I showed you at the very beginning should also make sense, that you can move the dx. Because could you solve this for d theta over dx? Yeah, you could. You have a derivative of theta with respect to x. It's the same exact idea, just a little bit different. A little bit different in how we structure the problem, but not the ideas are the same. So we had dx, now we have this cosine theta d theta. The reason why we use tangent and sine and secant is because on that right triangle, there's identities kind of built in. If you use the sine, the tangent, or the secant, they work out really nice. For instance, 1 minus sine squared theta is cosine squared theta. So this guy is cosine squared theta. Square root of cosine squared theta is cosine theta. These are gone. All we're going to have is y equals an integral of d theta, or 1 d theta. Y equals theta plus c. How in the world am I going to do that? That's what our substitution's for. If sine theta equals x, then theta, by definition, has to equal sine inverse of x. So what we have is y equals sine inverse of x plus c, which is nice. Now, the last one. Sometimes you run into stuff that you haven't practiced in a long time. I want to kind of repeat the idea of these are old concepts. We've used them, but if you've had Calc 3, you don't do a whole lot of this last one in Calc 3. Sometimes you forget, or it's not coming to mind. So if you have something that you know you should be able to do with an integral, and you go, well, it doesn't look like when I take an integral of both sides, a substitution. Right, it's not. It doesn't look like a trig sub. Definitely not. It doesn't look like anything that is easy for us. Maybe you're dealing with an integration by parts, and that's what we have here. For integration of parts to use, some people use lipid, a way to think about through what you would take as your u, what you would take as your v. What you want is for the derivative to become easier, and for the integral of what's left over to be possible. So when you're dealing with integration by parts, one of the first things I'll do is I'll look at this and say, I need one of these things that are connected by multiplication to become u. I need that u to be something I can take a derivative of, and generally it becomes easier, typically. I also need the integral of whatever's left over to be possible and to not get worse. You don't want that to get worse on you. Otherwise, if you pick the wrong thing, you'll tell really quick because your problem will start to explode. Oh man, that looks way worse. Let me keep going at it. Don't keep going at it. You probably made the wrong choice. So when I'm looking at this, I know this is why. Well, on the right-hand side, I need to pick one of these pieces, the things that are connected by a product here, to be u, and the rest of it's going to become v. So the way I was taught, the way that I have taught you, if you watched it, I will pick u as x. I cover that up. So I go, okay, x is gone. V is integral of whatever's left over. So v is everything else. If we actually do that integral, you don't need a plus c here. If you did a plus c, you would wrap that up later on with a larger plus c. You don't need one right there. So we know that.
Hi, it's Mark Barden from Sandy Hook Promise. The shooter who murdered my sweet little Daniel
Y equals u times v u is x, v is negative e to the negative x. You do that integral, you're going to get it's like a basic u sub. U would be negative x, the derivative of that is negative 1. So you have a negative floating in there. That's going to come out right there. So u times v is negative from here, x times e to the negative x. So u times v minus the integral of v du. Which means you need a du. The du comes from your substitution for u. So if u equals x, du equals, in this case, dx. So we pick something that the derivative generally gets easier. The rest of it should be an integral that's possible. We integrate and we derive. So we have u times v, got that, minus the integral of v du, kind of flip-flopping here. That's the first part, negative x, e to the negative x, minus this right here, that integral. Well, the integral of e to the negative x is negative e to the negative x, but we have a negative floating out front. So we're going to get positive e to the negative x. So minus is that minus. This becomes actually positive e to the negative x. And then we do a plus c. Now we can start factoring out. If you want to factor out a negative e to the negative x, this thing looks pretty good that way. And what we have is a general solution. In every one of these cases, We started with a derivative equals a function of x with no y's. I know I've said it like 10 times, but it's important you get that in your head. Those are the basicest, I think I just made up a word, the most basic differential equations. They're done with integrals. Move the dx, integrate both sides. You don't even have to move the dx, but integrate with dx on both sides. Take an integral on both sides. On the left-hand side, you're just going to get y, the solution, what you're looking for in the first place. On the right-hand side, you should have an integral that is possible. Doesn't have to be easy. They can be quite difficult. Most of the time in a section, like in a textbook, if you're working through a textbook right now, they'll give you a lot of different techniques like I did. So I gave you some basic ones, some substitution, some trig sums, subs, some tables, and then some integration by parts. Get used to that. Just for us to practice. So what we've done though, what's important for you guys to grasp right now is that all of these solutions are general solutions. They all have a plus c. They're all creating this, I'm just going to pretend they're all parabolas. I know they're not. But we create this family of curves. It's infinite. If you add plus c, it's just a vertical shift. So you could have like plus 1.00001 plus 1.00002 plus 1.00000, I lost count of my zeros, 3, and you could have these things just stacked right on top of one another. The key point here is that none of them, all of them are parallel. None of them share any points. What that means is that if we give 1 point, you say, well, I want to go through that point right there. There's only going to be one curve in that entire family that does that. It's going to be one particular solution out of the general solution, one particular curve out of the family of curves. So let's do that. Let's augment these problems with just some initial values right now.
I started a business to give old clothes a new life, and Chase has supported me from the beginning.
At least SafeLight can come to you for free.
They can come to me for free?
That's right. SafeLight can come to
So the first one, let's suppose that given our differential equation, we have our general solution, we know it's a plus c, it's a family of curves, but I want the one curve that goes to the point 2, 1. 2 comma 1 would look like that. Y of 2 equals 1. X would be 2. The corresponding Y value would be 1. That's a point, 2 comma 1. So this is asking for the curve that goes through the point 2 comma 1. It's all that's saying. If you remember from a couple of videos ago, we started thinking about particular solutions. We solved for some C's. It's the same exact stuff. In fact, it's basically the same lesson. It's just now you have one technique to be able to find the solution. Before we verified it and then we plugged in to solve for C. Now we just have to solve for C because we've already found it ourselves. So we replace X with 2, Y with 1. It's going to solve for C. We plug that back in. In our case here, if X is 2, 2 minus 2 is 0, 0 cubed is 0, 1/3 times 0 is 0, plus C is C, and we know that that's 1. So C equals 1, and then all we do is rewrite that. That's no longer a general solution. That's a particular solution. That says that this is the one curve that satisfies that differential equation, but also goes through that one point. Do you see the difference? I hope you see the difference in that. That this is a particular. It's no longer you can plug in anything you want and get a different curve that satisfies a differential equation. There's now one, and that plus C is all it takes to say this is the one curve going through that point. That's kind of cool. Next one. Let's suppose that we have. The fact that we need to go through the point -4, 0. All right, we've already done the entire integral, but down here, right at the very bottom, we know that y is 0 when x is -4. Let's see, 16 plus 9, 25 to the 3/2 power. When you do like 3/2 power, that half is the square root. So how I always do this, I don't take 25 to the 3rd power and then take a square root. That's crazy. What I do is I take 25 square root power, well, 1/2 power, and I get 5 and then I cube it. So it's 125. So 125 over 3. If I subtract it on both sides, we get a really awkward C. Check that again. 25 square root is 5 cubed, 125 over 3. Subtract both sides. We now know C is -125 over 3. Well, this one shouldn't be too bad. Let's suppose that on the next example, this derivative equals 10 over x squared plus 1, that we need to go through the origin. Y of 0 equals 0. Y is 0 when x is 0.
Still applying for jobs without tech skills? Let's fix that. Learn Python, SQL, Power BI, and more on DataCamp.
Tan inverse of 0. Oh man. Do you remember what that is? Tan inverse of 0. So if I do what angle tan inverse of 0 equals theta, so tan of theta equals 0. Do the inverse. Then we think that's sine over cosine, sine 0 at 0. So let's just pick 0. So tangent of 0 gives us 0, so tan inverse of 0 is also 0. So once you think through that stuff. C is 0. So our original solution here has a plus C of 0. And that's it. Okay, second to last one. Let's suppose on this we got to go through the point 0, 0 again. We do the same thing. Sine inverse of 0 is still going to be 0, so we would have no plus C here as well. Let's that's kind of the same exact example. Let's do the last one. Last one's kind of interesting. We want to go through the point 0, 1. So if we go through the point 0, 1, that says that y is 1 when x is 0. Be careful on the little math. It sucks so much to know how to do all this stuff and then to make a little error down here. It's just going to be kicking yourself off. I hate that. So let's really be careful. 0 plus 1 is obviously 1, but e to the negative 0 doesn't make any sense, but e to the 0 is still 1. So you have 1 times 1, but it's negative. So c is not 0 here. This is 1 equals negative 1 plus c. If you add that 1 to both sides, c is 2. So we get a particular solution from a family of curves that goes through that particular point, 0, 1. I hope this is making sense to you. Long story made short, how we deal with this is if you have a derivative that's equal to a function of x with no y's, try an integral. Usually they work pretty nicely, and then that's a general family of curves. You have this plus c, parallel families here. If you want it to go through one point, that's called an initial condition, and there's only one curve that satisfies that, a particular curve, a particular solution. So man, what a good idea would be is to try some of these right now before we go into the next video. Make sure you understand this concept, because we're going to kick it up a notch and start talking about how, well, acceleration and velocity are derivatives that are related to one another, to the position. We're going to start talking about how to do that. So get this stuff down so the next stuff makes sense. Hopefully you got it. I will see you for the next video.
When your kid is hurting and there's nothing you can do about it.
Hey there. Let's get going on another